Okay, welcome to the last video on part 1, Formulae, and we're not going to look at Formulae, and we're just going to look at a couple of examples, but just maybe remind ourselves about some things we may or may not remember. So, horizontal lines. Let's draw ourselves a nice horizontal line, and we're just looking at gradients is what we'll remind ourselves here. So the gradient of this not so horizontal line, maybe if it went straight across, well, gradient is rise of a run. How far up are you going for every one step across? Well, we're not going up or down at all, so our gradient's 0. Vertical lines, well, that's a line that's going kind of straight up and down. Well, our gradient is, remember, it's rise of a run, so we're going, well, for every one step across, but we're not going across. So we're trying to divide by 0. Oh, that's no good. So our gradient here is undefined. It's not that it's infinitely big or infinitely negatively big. It's undefined because we're not running at all. So let's just leave it at that. You can definitely explore more reasons if we want to. Okay, parallel lines. If we had, two lines like that were parallel, apart from the sad fact that they'll never meet, or if we had these two lines over here, and this is line 1 and 2, and maybe this is line 3 and 4, well, the gradients of parallel lines are equal. M3 equals M4. And that's clearly the same if the lines are like that, if they're horizontal, because both gradients are 0. And if we've got two vertical lines, well, both gradients are undefined. So they're not really equal, because how can two undefined values be equal to each other? But they're certainly parallel. Maybe some special cases. Okay, perpendicular lines. So if we had something like this, then if we've got line 1 and line 2, then when we multiply these gradients, we'll always get -1. Nice little extra exploration if you want to prove why that's the case. Using trig is a nice way to do it. Otherwise, you can do it straight with gradients, but leave that for you to do. And just bear in mind that if we've got a vertical and a horizontal line, well, clearly when we multiply their gradients, we won't get -1 because this is 0 and this one here is undefined. So again, special case that you can't multiply these two gradients because the one is undefined. So, and a special case, but in general, their product is -1. Okay, so collinear points might be a new concept. That is, if we've got 3 points, and we say that those 3 points are collinear, what it means is that they all lie on the same straight line. So if we've got these 3 points, A, B, and C, they all lie on the same straight line, which means that clearly the gradient of any section of this is going to be the same. So we're looking at gradients. The gradient from A to B is the same as the gradient from B to C. It's also the same as the gradient from A to C. It doesn't matter which 2 points you choose. Look, the steepness, the gradient is the same. Okay, so those are our main concepts, and we've got 2 examples to play around with them. Show that the triangle with vertices ABC is right-angled. Okay, so sometimes useful, maybe not. Our last sketch didn't seem to help us too much. And that is A is -5, -2, somewhere over there. B is 3, 4, somewhere up there. And C is 6, 0. Maybe it's more over there, I'm not sure. So, I don't know. If I draw my triangle, it looks like B is going to be where the right angle is. But I'm not quite sure that my sketch is reliable enough. But I'm going to try to see if the right angle's at B first, because it looks like the one worthwhile trying. Okay, to show if it's right angled, well, we're going to need our 2 gradients, right? So we're going to need this gradient AB, and we're going to need the gradient BC. And we can see if we multiply them together and get -1, great stuff. Then it must be a right angle. But that's what we're trying to see. And as I said, my sketch could be terrible. That might not be where the right angle is. So let's have a look. Gradient AB. Well, remember I already said I like going rise of a run. So from A to B, I'm just going to highlight and then I'm going to rub this out. I like to run in a positive direction. From -5 to 3, I'm running by 8. You're welcome to use the formula. From -2 to 4, I'm going by 6. So if I simplify that, 3/4. Okay, next up. Remember, pause, rewind as necessary. Okay, so let's have a look at, that was A, B. BC we thought would maybe be the other one. But if it's not, well, then we'll look at the last option, AC. So, rise over run. Well, we're going from B to C. So for this one, let's have a look here. I like to run in a positive, so from 3 to 6, I'm running by 3. Right, 6 minus 3 is 3, otherwise just be going by 3. 4 to 0, well, that's in a negative direction, fits in with our sketch. So 4 to 0, I'm running by -4. Okay, well, I can already see that we found the right one, that those two lines are indeed perpendicular, because 3/4 times -4/3 is -1. So therefore, AB is perpendicular to BC, or it is right angled at B. We might say that in two different ways. My writing's getting worse here. Right angled at behind my head, at B. Okay, so at B. So we found it. Now, one last thing to maybe think about here is, well, notice that this first gradient is the negative reciprocal of the second gradient. So 3/4, we've just flipped it around, makes it 4/3. The one's positive, the one's negative. Of course, if the one's positive, the other one has to be negative, because you can't have two positive gradients that are going to be at 90 degrees. Okay, so I think we have one final example. Determine T if these are collinear. Okay, so collinear, remember, says that the gradient between A and B is equal to the gradient between B and C is equal to the gradient between A and C. Now, we need to work with one gradient we know and one we don't. So I think it's going to be easiest if, let's work out this gradient here, A and B. So I'm going to go from A to B, MAB. Well, I always like to just write rise over run, remember? So rise over run, well, from A to B, I'm running by 2. But let me just keep my wits about me here. Earlier I said that I like to generally have the T somewhere, so it's T minus. So I definitely want T minus 3 on the numerator, rather than 3 minus T. Just feels easier to work with. As I said, maybe that's a terrible reason. Maybe I should push myself and go 3 minus T so I'm more comfortable working with that. But I'm going to say T minus 3, which means I must go 0 minus -2 to give me 2. Just want to make sure that's the right way around. I don't have a -2 here. I've got T minus 3, so 0 minus -2. Okay, and now we need a second gradient. I think it's going to make sense to go for AC, because then we know what that is. So the gradient of AC is rise over run. And we're going from A to C. So maybe I'm going to go from, let's go kind of A minus C this time. So -2 minus 1 is -3. 3 minus 1.5 is 1.5. And calculator if you want it, or I think I'm just going to say 1.5 goes into 3 twice. So this must be -0.5. Just want to keep things as simple as possible while we can. And we know that these two gradients must be equal to each other because these points are collinear. So -0.5 equals T minus 3/2. And that made life easy, because this means that -1 equals T minus 3. Add 4 to both sides, or think what -3 gives us -1. So I think that's going to give T equal to 2. Okay, and we could maybe sketch this and see if that made sense in some ways, but I think that one kind of works. I should probably have checked it out here, but this 2 minus 3 gives us -1/2. It seems to look reasonable. So there's our final answer. I don't think a sketch is necessary here. So that ends part 1. And at the end of every part, there's an exercise to do. So enjoy exercise 1. I've got it up on the screen here just in case you don't have ready access to it. So you can have a look, pause to get them down, and enjoy. I'll see you in part 2.